Hello everyone, welcome to Mutlu Learning Hub. In this session, we'll explore gradient descent, part 2 of our linear regression series. We'll see how models learn by adjusting their parameters to make more accurate predictions. Let's quickly recap linear regression. The goal is to find the best line that predicts outcomes from inputs. We start with a random line and make predictions for our data points. Here in this plot, this is our random line. And for example, the prediction for this point is here. Then we measure the errors, the differences between the predicted and actual values. Let's look at our graph again. Here is the error. This distance is the error. Using these errors, we adjust the parameters beta 0 and beta 1 to minimize the cost function. The cost function, also called mean squared error, sums up the squared differences between predicted and actual values. Squaring ensures we only get positive contributions and penalizes large errors more strongly. Mean squared error measures how far our predictions from actual values. Smaller values mean our model is making better predictions. For linear regression, this cost function is convex, which means it forms a smooth, ball-shaped surface like this. Because of this shape, there is only one minimum, called the unique global minimum, where the model achieves the best possible parameters. There are no other local minima, so if we move in the right direction, we are guaranteed to reach this optimal solution efficiently. The big question is, how do we actually find that minimum? Let's say we started with random beta 0 and beta 1 and computed the cost function, and we are here. How do we decide where to go and how do we reach to the minimum? It's worth noting that not all cost functions are this simple. In more complex nonlinear models, cost functions can be non-convex with many local minima and saddle points, making optimization much more challenging. Now, let's see how we actually minimize the cost function. Let's look at a simple example of minimizing the cost function. We start with a few data points, 1, 1, 2, 2, and 3, 3, and we want our model to learn the best line y equals x. So we start with a random line y equals beta 0 plus beta 1 x. Then, to make it simple, we fix beta 0 as 0, and we have now y equals beta 1 x. Now we are going to calculate the cost function. What we are going to do is, in fact, if we have a random line passing through the origin, we will calculate the sum of the squares of the differences, and then we will divide by 2m. Here m is 3 because we have 3 data points. Let's begin. So the cost function is 1 over 2 times 3, m equals 3, because we have 3 data points. And then we write down the line formula minus yi. So this is the sum of the square of the errors. We have 1 over 6. First data point is 1, 1. Its x coordinate is 1, so I have 1 here. And then 1 again. Square of the error plus the second data point, beta 1 times 2 minus 2. And then square, beta 1 times 3. Minus 3, and then square. If we look at the sum here, we have the common factors 2 and 3 there, so I'm gonna organize it. We have square of beta 1 minus 1, and then 2 square times beta 1 minus 2 square plus 3 square times beta 1 minus 1 square. And then we look at our equation again. We have the beta 1 minus 1 square as a common factor. So we get 1 plus 2 square plus 3 square divided by 6 times beta 1 minus 1 square, and it is 14 divided by 6 times beta 1 minus 1 square, and 2 is a common factor here, so our cost function is 7 by 3 times beta 1 minus 1 square. Now let's see the graph of the cost function. As you see here, the cost function forms a smooth ball-shaped curve, a convex function with one unique minimum. Now we need to start with a random beta 1 value. Let's start with beta 1 0, and I will just put 0 here to understand the iteration. So we started with this line here, y equals 0, and the cost function is sum of the squares of these distances divided by 6. Since we already calculated our cost function, I'm just gonna plug in here 0, so we get 7 by 3. If we look at the cost function graph, it's gonna be here. Now we want to minimize the cost function by changing beta 1. From the graph of the function, we can see that if we want to reach minimum, we need to move right. But how can we understand when we need to move right and when we need to move left? We can look at its derivative. If the derivative is positive, it means that the function is increasing, so we need to move left. And if the derivative is negative, it means the function is decreasing, so we need to move right to reach the minimum. At the point where the derivative equals 0, we reach the minimum. Right now we know our cost depends on the parameter beta 1, so the key idea is simple. If we change beta 1, the cost will change. And we want to change beta 1 in the direction that reduces the cost. To figure out which direction that is, we look at the slope of the cost function. And the sign of the derivative tells us which way to step. So to update beta 1, we take a small step opposite to the gradient. That's how we move downhill. And that leads us to the gradient descent update formula here. And alpha 1 is the learning rate. It controls how big each step is. We repeat this over and over until the slope becomes 0, meaning we've reached the minimum. Now let's calculate the derivative. Here is our cost function. So it's gonna be 7 by 3 times 2 times beta 1 minus 1, which is 14 divided by 3 times beta 1 minus 1. Let alpha be 1 over 7. I chose this to make our calculations easier. Now let's calculate the next beta 1 and apply this formula here. So beta 1 1 equals to our first beta 1 0 is here, which is 0. Alpha is 1 over 7, and we plug in the value 0 in the derivative. So we get 14 divided by 3 times 0 minus 1, and we get 2 divided by 3. Let's summarize what we have done so far. We started with the line y equals 0, and our first beta 1 was 0. Then we calculated the cost function, mean squared error. It is the mean of the square of the errors, and it is 7 by 3. We see it here on the plot. To reach the minimum, we want our point to go down. It means that we want our beta to move right. And to do that, we updated our beta 1 in the opposite direction of the gradient. And we got 2 by 3. If we plug in that point here, we are there. And now our new line is y equals 2 by 3x, which is here. And now again we are going to calculate the cost function, the mean of the squared errors. And using this update formula, we are going to update our beta 1 again. If we plug in 2 by 3 in the cost function, we obtain 7 by 27. On our graph, it's here. 7 by 27. And so we still want to move right. We want this point go down and reach the minimum. So we calculate the derivative. We plug in 2 by 3 in this formula. So we get 2 by 3 minus 1, which is minus 14 divided by 9. Now we are gonna use the update formula, this formula. Our next beta, I'm gonna call it beta 1, 2, will be beta 1, 1 minus our learning rate 1 over 7 times the derivative of the cost function at the point 2 by 3. Let's do the calculation. Beta 1, 1 is 2 by 3, our learning rate 1 over 7, and then the derivative at 2 by 3, we got minus 14 divided by 9, and we get 2 by 3. Here 7 is a common factor, so we get 2 by 3 plus 2 divided by 9, which is 8 divided by 9. So this is our next point, 8 by 9. And you can easily calculate that. The cost function at 8 by 9 is 7 divided by 243. Now let's see it on the graph. So after the second iteration, we obtain the line y equals 8 divided by 9x. So we get closer to our points. Let's look at our cost function. Now our point moved here, but we still want to reach minimum. So let's do one more iteration. The derivative of the cost function at 8 by 9 is minus 14 divided by 27. Now we calculate the next beta 1. Beta 1, 3. So our update formula is beta 1, 2 minus our learning rate 1 divided by 7, and the derivative at 8 by 9, which is minus 14 divided by 27. If we plug in the values, we get 8 by 9 plus 1 by 7 times 14 divided by 27, and here 7 is a common factor, and then we obtain 8 by 9 plus 2 divided by 27, which is gonna be 26 divided by 27. And then if we plug in this in the cost function, I already calculated this, you're gonna obtain 7 by 3 times 1 over the square of 27. It's gonna be approximately 0.003. Now let's see these points on the graph. Our new beta 1 is 26 divided by 27, so our new line is y equals 26 divided by 27x. It's here, so we got closer to the line y equals x, and on the cost functions graph we come closer to 0, As you see, our point is moving down and our beta 1 is moving right. We continue updating the parameter while the gradient remains significantly different from 0. Once the gradient approaches 0 and updates no longer reduce the cost, we declare convergence. Here, alpha is the learning rate. It decides how big each step is as we move downhill. A tiny learning rate means tiny steps and slow learning. A huge learning rate means wild jumps that could miss the target completely, so we want a learning rate that's just right. Now we'll look at what happens when we want to update both beta 0 and beta 1 together to get a better line. We begin by choosing a random line. It's just a guess for how the data behaves. It may sit too high, too low, or at the wrong angle. That randomness is okay. The important part is that we now have something to improve. Here we bring the cost function. This surface shows the error for every possible combination of beta 0 and beta 1. Each point on this surface represents a different line. For example, if our starting line has high error, that means we begin somewhere up here on the slope. The gradient descent asks in which direction should we move beta 0, beta 1 so that the error goes down. Here, when I say gradients, I mean the partial derivatives with respect to beta 0 and beta 1. The gradients give exactly that direction. We update the parameters by taking a small step guided by the learning rate. With each step, we slide lower on the surface, gradually improving the line. We keep going until we reach the bottom of the valley. That is where the error is minimized and our line fits the data as well as possible. And this algorithm is called the gradient descent algorithm. Let's wrap up. Gradient descent is an optimization algorithm used to find the values of beta 0 and beta 1 that minimize the cost function. We start with a random line, just an initial guess. Then we compute the gradient, which tells us how the error changed with each parameter. By moving opposite the gradient and taking steps controlled by the learning rate, we gradually reduce the error. We repeat this process until the cost function reaches its minimum, and the result is the best fitting line for our data. Once we have a model, we need to check how well it fits the data. In the next video, we'll cover evaluation metrics like R-square and adjusted R-square, which quantify how much of the variation in the data our model explains. Thank you for your attention. I hope this gave you a clear understanding of gradient descent and how we use it to train models.